Hi everyone. Now we are going to discuss about one other important applications of Schrodinger's wave equation on solving the wave function for simple or linear harmonic oscillator. So you already known well what is a linear harmonic oscillator. Is nothing but we have a spring-like mechanism which is connected with one end, whereas the opposite end is connected with a mass m. So it has informed that, or it is inferred that there is no more friction between the mass to the plane, and then with respect to the force acting on the mass, we say about the stretching, we say its amplitude. So we have a chance of that a spring have to move back and forth by the connecting with the mass. So we are expecting the back and forth movement of the mass with respect to the force acting on the system. So whenever you are applying a force on the mass m, that mass stores its energy as its potential energy, by means that while we are releasing of the force, the mass tries to come back to its original position. So with respect to the turning points, as we said, is amplitude on positive and negative side, we have a chance of an oscillation is going to be started, and then that oscillation will have a back and forth movement for a longer time with respect to the frictionless property of the mass over the plane. So while we are applying Hooke's law, the force acting on a mass will be equal to minus of kx. So we say k is a spring constant and x is the linear restoring force. We already known by using of Newton's second law, F equal to mv. So when we are just matching up these two equations, then we can achieve the final equation of m is nothing but mass into acceleration. So m into x double prime represents the acceleration and will be equal to minus of kx, what we already derived by using of Hooke's law regarding linear harmonic oscillator. So while you rewrite the term, so you can get d square x by dt square will be equal to minus of k by m times of x. Otherwise, the solution of the linear restoring force x of t will be equal to a is nothing but the amplitude a sine k by m power 1 by 2 into t. Okay. So linear harmonic oscillator is oscillates sinusoidally, whereas a is how far the spring is stretched initially, and by means of a we are achieving with turning points as a into minus a. So all the energy utilized on this system is potential energy. So whenever you are just working with the potential graph with respect to the position of x, we already known then when the particle started oscillation, so we know that it start back and forth movement. So we already known that the total energy utilized on the system is potential energy. So we find that the particle will move to the extent we say about its a potential well, where the chance of particles moving back to this limit, moving over the limit of the turning point is not at all possible. So we say the infinite potential is required to cross the limit. So we have a chance of the particle will try to come back to its real position. That's why we have back and forth movement. So this movement is started, and then you know well because of the friction over the surface, we are achieving with certain degrees in the region of oscillation, and one fine stage the particle come back to its rest position. So by using of the energy calculations, we can say the potential is parabolic in nature. And then if you just calculate what about the force acting on system will be equal to minus of dou vx by dou x. So you already known well the potential vx will be equal to integral of kx into dx. So otherwise you can get the term the potential energy vx of the linear harmonic oscillator will be equal to 1 by 2 times of kx square. So here k we represent as a spring constant. So we have a value of it is 4 pi square m into nu square. So we already known well omega equal to 2 pi nu. So I can best utilize 4 pi square nu square as 2 pi nu square. So I can get it is omega square. So the spring constant k will be written as m into omega square. So you see nu is the oscillator frequency in hertz, whereas omega is the oscillator frequency by radians per second. So by means that we can say the energy of the oscillator will be equal to 1 by 2 times of Ka square, whereas A is the classical turning points. So you just notice that A may take any value by means that energy is continuous and we have continuous range of values achieved till reaching of 0. So we just think about the case, is it possible to have a system with 0 energy? So it is not at all possible. Then how we have to confirm with harmonic oscillations? So the best example is, or you say the simplest model for harmonic oscillations is molecular vibrations. So you just think about the case, the bonding between the atoms will act as a springs. So near bottom of molecule is potential well. So molecular potential is approximately parabolic. We just find that we have a chance of molecular bonding will be there with respect to the energy supplied to the system. We say about stretching of the molecules. The atoms start vibrating in the molecules by means that we are achieving with molecular potential energy as a function of atomic separation. So that's why we say it is quantum harmonic molecule or quantum harmonic oscillator. So I already told you that there is no chance of we are getting the particle to get stationary. Why we say like this is, if you say x equal to 0, then we can definitely say the value of momentum P will be equal to m into v. It is also equal to 0, because you know v is nothing but the velocity is nothing but distance by time taken. So where you consider the position of x equal to 0, then definitely v will be 0. So once you say v will be 0, and you can say definitely the momentum p is also 0. So while using of x and 0 and p and 0 in de Broglie's hypothesis, then you say about the uncertainty in position and momentum will become 0. So you just notice that the value of delta x and delta p must be 0 if you consider the position of the particle at rest position. So it won't be happen for a quantum harmonic oscillator. Why? Because if it is happen in a normal classical mechanics system, then if you are applying with the quantum mechanics, definitely it won't be applied, because if it is applied means we are just neglecting, or we are just say about neglecting the condition of de Broglie's hypothesis. So we already known well all the quantum systems obeys de Broglie's hypothesis. So uncertainty principle indicates that minimum quantum harmonic oscillator have energy, otherwise energy may not be 0. So you just notice that the turning point have a 0 kinetic energy, whereas it have maximum potential energy. So classical particles can never be past turning point, whereas quantum mechanical basis we have a chance of the particle will have a continuous amount of energy and then it doesn't reach with 0 point. So that is the importance of quantum harmonic oscillator. Now we are start deriving the wave function of a quantum harmonic oscillator. So for that we already told that we are just going to utilize Schrodinger's wave equation. So we just take time independent one dimensional Schrodinger's wave equation, dou squared psi by dou x squared plus 2m by h cross squared times of E minus V into psi. This is equation number 1. So we already known well the potential energy of the linear harmonic oscillator will be equal to 1 by 2 times of kx squared. So now I substitute this term here, I will get this equation 2. So you just insert the term of 2m h cross squared in these two part of the value side, then you got the equation like this. So you just notice these two terms are constant on with respect to its values, where you say m is the mass of the particle, E is the energy of the particle, h cross is also constant, and k is also a spring constant. So each and every part of these terms are constant, by means that if we take mk by h cross squared as alpha squared and 2me by h cross squared as epsilon, then the equation will be written like this: dou squared psi by dou x squared plus epsilon minus alpha squared x squared times of psi, which is equal to 0. So that is equation number 3. So now you notice this equation 3. So it have spatial coefficient and it never get a possible solution of psi. Because why we are just getting up this solution, while we are going with the second order differential equations, we can achieve with the solution of the wave function of a linear harmonic motion. So you already known well the range of x will be in the order of minus infinity to plus infinity. Why? Because of if you consider this place, the particle will have a chance to move back and forth, and we couldn't define what is the exact position of the particle with respect to time. Why? Because of that oscillation will be back and forth and it is continuous in motion, by means that even you couldn't define the exact region of particle where it is oscillating, and definitely we couldn't define with what is the exact position of x. Okay, so that's why we say there is no chance. There is a chance of the range of position of the particle x will be in the order of minus infinity to plus infinity. So while just accepting of these terms, the solution must be obeyed with Bound's approximations or Bound's conditions. So the first condition is the wave function must be finite everywhere and it should be of single value, and we already known that the wave function should represent the continual nature of the energy system, and the first derivative of continuous have to be followed. Okay, so these are the four important conditions must be obeyed while we are deriving with the wave function. So for that we started using of polynomial method. So for determination of psi of x, the wave function of a linear harmonic oscillator, we just consider the term x to be tends to infinity. So introducing a power series to make the large value of x to be related with all the smallest portion of the distance between, or you say about the position of particles in that region. So by means that we just take the equation number 3 again. We say about dou squared psi by dou x squared and plus epsilon minus alpha squared x squared to the power or to the product of psi will be equal to 0. So in this case, if we assume x is tends to infinity, then what is happening up in the second term? Just notice that it is x will become infinity, by means that the second part have the maximum value while comparing with the first term. So we can neglect the term epsilon, by means of we are achieving with asymptotic form of the equation number 3 as dou squared psi by dou x squared minus alpha squared x squared psi equal to 0. So now we got certain nominal form of second order differential equation, by means that we can achieve the solution of this equation number 4 as psi of x, the wave function of a particle in linear harmonic motion, will be equal to exponential of plus or minus alpha x squared by 2. So this is equation number 5, which gives a solution of linear harmonic oscillation. Okay, so now we have to confirm is this relation is exact on defining the condition of linear harmonic motion as per the conditions derived by Max Born. So now we just start deriving differentiating equation number 5 with respect to x. So this one is a somewhat tedious process, so it is given step by step process. You just notice, if I go with differentiation of equation number 5 with respect to x, so we know well its unidirectional motion of the particle is only on x axis alone. So we say dou psi by dou x will be equal to, if I differentiate of this term, what I will get? So I just got the term as it is, exponential term as it is, and if I differentiate that internal part of the exponential, then I can get alpha x squared will be written as alpha into 2x and divided by 2 as it is. So now you find that these two, the term 2 is available on both sides, on numerator and denominator, it will be cancelled, by means that I can get dou psi by dou x, differentiation of the wave function psi with respect to x will be equal to e power plus or exponential of plus or minus alpha x squared by 2 into alpha x. Now we just differentiate this equation one more time with respect to x. So I can get dou squared psi by dou x squared into e power plus or minus alpha x squared by 2 into alpha x. We just notice that these two terms have its own variables of x. So I just differentiate, go for partial differentiation of maintaining one more term as constant. You just notice that for the first time I just make this term e power plus or minus alpha x squared is constant, and then I differentiate the second term alone. So I have a term alpha is constant. If I differentiate x, so I can get dou x by dou x, and then I have one more constant of plus or minus. So here I just make the second term as constant, alpha x is constant. So now I differentiate the term of exponential of plus or minus alpha x squared by 2. So I can get the term of, I already known well, I will get the term as it is, and then if I just differentiate the power term alone, so I can get it is alpha 2x by 2. So once I rewrite this equation, so I get this one, because dou x by dou x will be cancelled. Likewise 2 and 2 will be cancelled on both numerator and denominator, by means that I got the simplified equation of like this. Okay, so if you see, or we can see that on both terms we have a common exponential term. So once I take out the exponential term on both exponential terms from both terms, so I can get e power plus or minus alpha x squared by 2 is a common term. Then we can get it is alpha plus or minus of alpha squared into x squared. So this one is the value what we got for second order differentiation of the wave function psi of equation number 5. So we already known that if we go for a consideration of x tends to infinity, and we known well definitely the value of alpha squared must be much greater than alpha. So once I neglect the the first term of this equation, by means that I got the final term of second order differentiation of the wave function psi of x as we got from the differential part will be equal to e exponential of plus or minus alpha x squared by 2 into alpha squared into x squared. So you just find this term e power plus or minus alpha x squared is representing the wave function psi, by means that I can get the final solution of the term dou squared psi by dou x squared will be equal to alpha squared into x squared to the terms of pi. So now I just utilize this equation number 6 in equation number 4, where we got the general equation of wave function, second order differential equation. So you just notice, if I replace the term dou squared psi by dou x squared as alpha squared x squared psi, so you just notice these two terms are unique or similar, so I get a final term of 0. So you just notice that there is no meaning of the equation of motion, linear harmonic motion of a particle will become 0. We need a solution that must be of wave function, which helps us to understand the harmonic oscillation. So with these conclusions, we just notice that we are achieving of the wave function, what we achieved as a solution of the wave function is not at all enough to represent linear harmonic oscillations. So what it is expressed is, it is added that while considering the term of psi of x equal to exponential of plus or minus alpha x squared by 2, along with the condition of psi squared decreases with increasing value of x. So by means that we have to first consider either it is plus or minus. So once we consider the term e power minus, so once x is increasing, what is happening up? The term in negative will be increasing, by means that the value of psi of x will get decreased. So we can say that this condition holds good for condition of x tends to infinity. Otherwise, if you make x equal to infinity, so e power infinity will be 1. So you got some numerical values. Whereas if you go for the second option, if we apply with the positive term here, so if we say x is infinity, then the condition is not fit for the option of e power plus infinity will become infinity. So we have no more option of the finding of the solution of the wave function within the parabolic curve. So it is say not finite everywhere. So according to these results, it is confirmed that, or it is inferred that the term of e power minus alpha x squared by 2 is prompt enough to explain the wave function along with the term f of x, because you already known well, if we are adding of e power minus of plus alpha x squared by 2 never give a proper solution of a wave function of a linear harmonic oscillator. So one more term f of x, we say both the wave function f of x is added with the solution to get a prompt answer regarding what about the wave function of a particle which is going with linear harmonic oscillation. So by this equation number 8, we should find out the value for f of x. Now we just again doing the process, we have to start doing a process again. So now we got a term of psi of x equal to something, isn't it? So by this equation we just go for partial differentiation with respect to x. Once we go for partial differentiation, you just notice that we have these two terms related with x. So as usual, we just make f of x as constant, and then we just differentiate the first term. I got e power minus of alpha x squared by 2 into minus of alpha into 2x by 2, and then we have term plus e power minus alpha x squared by 2 is maintained as constant by the second term, and f of x is integrated, so differentiated, by means that we got the term f prime x. So f prime of x represents first order differential equation of f of x. So now we just notice that the final term of the equation will be like this. So dou psi by dou x will be e power minus alpha x squared by 2 into minus of alpha x into f of x plus e power minus alpha x squared by 2 into f prime of f of x. If we differentiate equation number 2 with respect to x again, so we just consider the yellow shaded line, we just yellow shaded box is a first term. It consists 3 terms, all these 3 terms having the term x. So that means that you have to make differentiation with respect to each term. So each and every time, the first time what you are doing is, I just differentiate this first term of e power exponential minus alpha x squared by 2 and I am making up other 2 terms constant. So whereas the second line I am just doing of making of minus alpha x squared differentiating, whereas making of first and third term constant. Like that I am doing by means that I got the final solution. So you just notice that if I go for differentiation of dou squared psi by dou x squared, I just maintained the yellow marking regarding the differentiation with respect to the first term alone. So you just seen that I just differentiate the first part of the first term e power minus alpha x squared by 2, and then if I differentiate this one I get minus of alpha x as I known already, and then I maintain these 2 terms as it is, plus and I maintain this term first and third term, whereas I just partially differentiate the second term alone minus of alpha into dou x by dou x. Likewise the third term e power minus alpha x squared by 2 minus of alpha x remain as it is, and then if I differentiate f of x I get f prime of x. So these 3 parts came by partial differentiation of the first term of dou psi by dou x. The same condition is applied for the second term also. So here you just notice we have 2 terms are there. In the second term we have 2 parts, one is exponential term and another one is f prime term. So once I go with differentiation of the first term, again as it is e power minus alpha x squared by 2 will be there, and then differentiation of that exponential term I got minus of alpha x, and then f prime of x will be there. Then I just added with one more term. So I just making up the first term as it is, and then if I differentiate the second term, so I can get f double prime of x. So now you just notice that we have a terms related with f of x, f prime of x and f double prime of x. So now I just rearrange the terms by means that I have to combine the equations with respect to f of x. So you just go with the case of the first term will be get like this, because you just see minus of alpha x will be there, by means that it is minus into minus will become plus. So we got exponential term along with alpha squared x squared into f of x. That's what we got here. Whereas for the second term, you just notice that we have minus will be here, so it is become negative. So minus of exponential of minus alpha x squared by 2 into alpha will be there, whereas dou x by dou x cancels, and then f of x will be there. So that it is written here. And regarding the third term, again you just notice we have exponential term as it is, whereas it become negative because of minus alpha x, and we have final term alpha x into f prime of x. So the same thing happened for the other 2 terms also. So here also it become negative, and then we got as it is of the final term. So you got the final equation like this. While you are going to rearrange these equations with respect to f of x and f prime of x and f double prime of x, you got the solution of like this. So in all these 3 terms, you just notice that we have a common term of e power minus alpha x squared by 2. So if I take this term is constant, then I can get f double prime of x minus of, just notice f prime of x, we have 2 options, alpha x and alpha x. So it is 2 alpha x times of f prime of x, and then it becomes plus alpha squared x squared minus of alpha into f of x. So I got this equation by recombining the term with respect to f of x, f prime of x and f double prime of x. So now we got the values for dou psi by dou t. This is just psi. We got the, so we have this equation psi. By following up this equation, I got the term. I have a value of dou psi by dou x and by following up that dou psi by dou x, I find out the value of dou squared psi by dou x square. Okay. So now we have to substitute equation number 9 and 10 in the general equation of linear harmonic motion what we derived. So we say that if you just substitute the value for dou squared psi by dou x square from equation number 10, so we got this term as it is. Whereas the term of psi will be written as e power minus of alpha x square by 2 into f of x what we derived from equation number 9. So while we are just removing the common term on both terms, so just notice e power minus alpha x squared by 2 will be common in both terms, so we are just removing out. On the right side becomes 0, so it becomes 0 only. That means that I got the final term of f double prime of x minus of 2 alpha x into f prime of x plus alpha squared minus into f of x minus of alpha f of x plus, because just taking into this term, so f of x will be there, so it is epsilon into f of x minus into minus will become, yes, here it is minus, so it is alpha squared x squared into f of x. So here you just notice that these two terms. So the first term came from the first part and the second term came from the second part of this equation. So these two terms are equal and opposite. So just cancel these two terms by means that we can get the final term of f double prime of x minus of 2 times of alpha x f prime of x. Because of this term is cancelled, so we have two terms related to f of x. So if I make the common term of f of x here, so I have, if I just make it as plus here, so I can get epsilon minus alpha is into f of x will be equal to 0. So if I want to write this term in standard form, so definitely we know that f double prime of x will be written as dou squared f by dou x squared, and the f prime of x will be written as dou f by dou x. So I got the general form or standard form of linear harmonic oscillator as it is mentioned in equation 11. So for to convert the equation number 11 into Harmonic polynomial function, it is assumed that y will be equal to root of alpha into x and f of x will be equal to Hermitian function h of y. So y differentiating equation number 12, you just notice that if I go with dou y by dou x, a differentiating equation y equal to alpha x, root of alpha x as x in respect of x, I can get dou y by dou x will be equal to root of alpha, it's constant, so I got dou x by dou x, so it is equal to root of alpha alone. So whereas if I go with differentiation of f of x, you just notice that there is no more term on right side with x. So what I will do is I simply rewrite this equation as dou f by dou x is equal to dou f by dou y times of dou y into dou x. So you just know this value of dou y by dou x is equal to root of alpha, by means that I can get the final term of dou f by dou x will be equal to dou f by dou y times of root of alpha. So if I go for second order differentiation, because I have a term related to y or x, so I go for second order differentiation. So if I write dou squared f by dou x squared, which I want to substitute in equation number 11, so I can get dou by dou x of dou f by dou x will be there. So you just notice that dou f by dou x will be equal to dou f by dou y times of root of alpha. So here you notice I have a term which is related with x, whereas here there is no terms related with x. So what I will do is very simple again, I just multiply and divide by dou y on both sides. So just rewrite this dou by dou x term as dou by dou y times of root of alpha, dou by dou x is there, and then again I am writing this dou y by dou x. So I know the value of dou y by dou x, it is equal to root of alpha, isn't it? So by means that I got the term of dou squared f by dou y squared will be equal to into root of alpha into again 1 by root of alpha, while you are substituting the value of dou y by dou x. So by means that I got the final term of dou squared f by dou x squared will be equal to alpha times of dou squared f by dou y squared. So now I am substituting the values what you got as dou f by dou y and dou squared f by dou x squared. In equation number 11 I got this term dou squared, just find equation number 11 is here, So I have dou squared f by dou x squared, it is there. So if I just replace this term as dou squared f by dou x squared as alpha into dou squared f by dou y squared. Okay. So likewise, I can easily replace the term dou f by dou x as what we derived it as 2 times of. So while substituting the values for dou squared f by dou x squared and dou f by dou x, what we got from the differentiation of the newer wave function, so you can get the term like this. So while you are substituting these two terms on equation of general equation, then in equation number 11 you can get the term, if I replace dou squared f by dou x squared as alpha times of dou squared f by dou y squared, I write like this, and minus of 2 alpha x as it is, and if I replace dou f by dou x as root of alpha times of dou f by dou y, I write that this term, and then I got as it is plus of epsilon minus alpha times of f, it is equal to 0. So if I want to just notice that on this equation all the terms are related to y, whereas only one term is available with respect to x. So now I replace this equation, this term with respect to y. So we already known that the term y is represented as root of alpha into x. So I can replace the term x as y by root of alpha. So once I replace the term x with y divided by root of alpha, so I can get the equation like this. So now you find the term alpha is there with respect to second order differentiation of the wave function f. So once I divide the term, this equation with respect to alpha, by means that I got the final solution of dou squared f by dou y squared minus of 2y times of dou f by dou y plus, you just notice here we have epsilon minus alpha will be there. So if I divide these two terms individually, so it becomes epsilon by alpha minus 1 into f, which is equal to 0. So you already known well the term epsilon and alpha are constant. So this term epsilon divided by alpha minus 1 will be taken as the term 2n. So this equation will be comprised as dou squared f by dou y squared minus of 2y times of dou f by dou y plus 2n of equal to 0. That is equation number 13. So now while we are replacing equation number 13 into variable form, because we have f is the wave function form, if we are replacing into variable form of Hermite polynomial as h of y, so f of x equal to h of y, so we got the final second order Hermite polynomial equation for the linear harmonic oscillator as dou squared h by dou y squared minus 2y into dou h by dou y plus 2n times of h equal to 0. So this equation number 14 is a standard mathematical equation known as Hermite equation for linear harmonic oscillator. So while it was found the solution of equation number 4 are called as Hermite polynomials and is given by hn of y will be equal to f of y. So it is equal to minus 1 power n and e power minus y squared times of dou double prime divided by dou y prime. So dou squared by dou y squared times of e power minus of y squared. So this equation number 15 is the solution of equation number 14, and the eigenfunctions of harmonic oscillator is therefore written as psi of n to the base of y, which represents the Hermite polynomial. The wave function with respect to Hermite polynomial is n represents n times of h n into the base y of exponential of minus y squared by 2. So here n is the normalization constant. So regarding the energy eigenvalues, we already known when the value of psi is physically accepted only when y tends to infinity, which leads to the wave function psi equal to 0. So but in the mere case, in the Hermite polynomial, h of y is more rapid than the degrees in e power minus y squared by 2. So which confirms our condition that the energy is continuous in nature. So once we consider the case of h of n into e exponential of minus y squared by 2 is tends to 0 only when the power series of h of y is finite. So this is a condition what is to be termed as continuous of wave function is accepted. Likewise, if you say the case, so while considering the case of epsilon divided by alpha minus 1 equal to 2n, so by this term we can get the term integral value of n will be equal to 1 by 2 times of epsilon by alpha minus 1. That's equation number 17. So now we known well the term of epsilon and alpha is already defined. So while you are substituting those values on this equation, so you can get 2me, because we say that epsilon will be equal to 2me by h cross square. So we just take as it is, whereas we say the case alpha will be equal to root of mk by h cross square. So by means that we are writing in reverse, so you can get terms equal to 2n plus 1. Otherwise, if I go for manipulation, I got the final term of 2e by h cross times of root of m by k equal to 2n plus 1. So we know this value root of m by k will be equal to omega. So by means that, so you just get the term of energy E will be equal to, I just rewrite this equation in terms of E, by means that we can say E will be equal to 2n plus 1 times of h cross divided by root of m by k. So you just have the case, if I rewrite this term root of k by m equal to omega in equation number 18, by means that you got the final term of energy E or eigen energy value of the linear harmonic oscillator E will be equal to 2n plus 1 divided by 2 times of h cross omega. So we already known h cross will be equal to h by 2 pi and omega equal to 2 pi nu. So that means that I got the final solution of the eigen values for the permitted value of total energy is given by E equal to n plus 1 by 2 times of h nu. Whereas we know the value of n will be started from 0 to 1, 2, 3 like that. So equation number 19 represents the total energy of the system. Whereas if you go with, so the permitted value of total energy is given by the term E will be equal to n plus 1 by 2 times of h nu. So we know well the value of n will start from 0 to 1, 2, 3 like that. So you just find the energy gap or energy values of the linear harmonic oscillator starts from 0. So if you say n equal to 0, then you can get the energy E will be equal to 1 by 2 times of h nu. So whereas if there is an increasing of the value of n, the values of energies also goes on increasing. You just notice that the wave function is continuous. So with respect to the moment of oscillation of the particle in the linear harmonic motion, we have a chance of the possibilities of an oscillation start from the maximum to the minimum, whereas we have no more chance of the value of x is equal to 0. So the energy of a harmonic oscillator is thus quantized in steps of h nu. So the energy levels hereby are eventually spaced, and then if it is noted that here n equal to 0, E naught will be equal to 1 by 2 times of h nu, which is the lowest value of the energy of the oscillator can have in the system. So this value is called the 0 point energy. Whereas if you consider in the harmonic oscillator of the wave function, we know well. So each wave function psi n consists of a polynomial h and y called Hermite polynomial function, and then the exponential factor of e power minus y squared by 2 and a numerical coefficient which is needed for psi n to meet the normalization condition. So by means that you can get the normalization of wave function of integral of minus infinity to plus infinity to the power of the square of psi n square dy equal to 1. So the general formula of the nth wave function for a linear harmonic oscillator is given by psi of n equal to 2 pi nu by h cross times of power 1 by 4 and 2n into n factorial power minus 1 by 2 and hn of e power minus y squared by 2. So this is the complete general solution for the particles which is on linear harmonic oscillation. So you just seen the first 4 Hermite polynomials of h and y are listed in this table. Just notice that with respect to the value of n equal to 0, 1, 2, 3, you just notice what is the Hermite function and what is about the energy waves. So you just notice that the energies keep on increasing with respect to the term of integral multiples of 1 by 2. So the vertical lines showing the limit of minus a to plus a. What about the wave function? If we say psi equal to 0, so we have half semicircle. By means of we have only one wave function is achieved in linear harmonic oscillator, whereas if you say for the function of psi equal to 1, you just notice that wave function goes on increasing with respect to increasing of wavelength, and then psi equal to further increasing of nodes are there, and then it just keep on increasing. So with respect to the increasing of the energy levels, so with respect to the value of integers, the energy levels goes on increasing, by means that we have a chance of maximum amount of energy is produced in the system of linear harmonic oscillator. So I think you understand this topic well. We'll meet you soon with the next topic. Thank you.